Hello. This video is about maximum power transfer theorem. Um, we have several cases to consider. We are going to apply this theorem to AC circuit. So to begin with, let's assume we have a circuit, and the circuit can be represented by a Thevenin equivalent circuit. And the load here is to be varied. We have many cases to consider. The first cases I would recommend is purely resistive load. Purely resistive load. This means ZL is equal to RL. There is no imaginary part in the load resistance. So now our goal is to vary the load resistance in a way that the power to the load is maximum. So what is the power to the load? So according to this diagram, the power to the load is going to be PL, and then I, magnitude of I, which is the current, and then times L, ROL, the resistance. There is no imaginary part in the load. So what is I in this case? I, in my understanding, is correct. I should be the, let's see, just make sure the order is right. I can be calculated by VTH divided by the impedance, the total impedance. So what is the total impedance? VL plus RL, VTH plus RL, RL. In this case, VTH is the Thevenin impedance, which basically include the resistive part and also the imaginary reactance. So the best thing that we do is to write down clearly ROTH plus RL, and then JVTH. So in this case, we can substitute I into this equation to get the power. So power in this case is VTH square and then RL, and then the magnitude of I, which is RTH plus RL plus VTH square. We want to vary the resistance at the low and find out the maximum power, the condition for the maximum power transfer. In this case, we can do this by setting dPL, dRL to 0. And if you do that, then we differentiate this expression with respect to ROL. And what we will get here is V TH square, and then multiplied by this term. And minus 2 RTH plus RL, and then times the top. And then obviously you need to divide the denominator square. So this one will be it will be like this. So let's simplify this expression and see what we can get. If you do that, very obviously, you can cancel off this term. So now let's simplify this expression for case 1. So you have this expression in the numerator, and both terms contain the absolute value of VTH. So if I do that, then we will have RTH plus RL square plus VTH square, and then minus 2 RTH plus RL. You also need to and this one is going to be 0. So if you simplify this expression, you will get ROL. If you take this one, factorize these two expressions, you will get RTH plus RL, and then this one RTH minus plus RL minus 2RL, and then plus ZTH. So very obviously, this expression, these two combined together is equal to, and then we have, so from here, we can say the load resistance should be RTH square plus ZTH square, and then square root. So the end result is very clear. In order to get the maximum power, RTH should be equal to this expression. In other words, the load resistance should be equal to this expression. So the load resistance will be equal to the magnitude of the tapping resistance. So this is the case one, so-called case one. Case one is purely resistive load. So we got this result and we saved it. And we are going to consider case two. So what is case two? Case two is complex load. Complex load. So the load here, ZL, will be equal to ROL plus JXL. Then we are going to calculate based on our understanding. So now, what is the current? The current is going to be the voltage, and then divided by the total impedance. I'm going to simplify this on the fly. The total impedance is going to be, and without writing another line of equations, I'm going to simplify this. So this is the current for the whole circuit. And this time we assume the load is the combination of real part and also imaginary part. The load is a complex load. So what is the power at the load? The power at the load is equal to the magnitude of I square and then ZL. But only the resistive part will consume power. So in other words, this equation can be repeated as And then so this is all. So the next thing that we need to do in order to find out the condition for the maximum power transfer. The next thing that we need to do is to find the derivative of PL against ZL. So the first thing that we can do is to find a derivative of uh, dPL against the RL, set it to 0, assuming that so uh, we do it separately. We first differentiate the power with respect to the low reactant and see what happens. And if we do that, then the top one will be 0. And, what we can get is 2 R, and then uh, and then the square of the top bottom expression. And this one is totally equal to 0. Based on direct inspection, we know that the in this case, for the power to be maximally transferred, uh, XL must be equal to minus XTH. So this is the first condition by setting dPL uh, derivative of power L against the XL equal to 0, the low reactant. So we say this result. The next thing that we are going to do is to find the derivative of PL, the low power, against RL, and set it to 0. And we are going to do that based on this expression. Now, if we do that, then the first term will be TH squared, the, and then multiplied by RTH plus XTH plus XL. And then the minus 2 RTH RL square, and then multiply by the top expression, and 0. And we have already found out in order for this maximum power transfer to occur. And we know that from the previous analysis, XL must be equal to minus uh, the Tegrin reactant. So if we do that, if we substitute to here, then this one will become 0. And what we have left here is this expression. And this one. And if we simplify this expression, what we will end up with here is RL being equals to RTH. So this is what we can get. Right? You can see that if you do that, then if you simplify the equation, right, you will end up with this condition. So in order to attain maximum power transfer, the low impedance has to have a mu part being equal to the mu part of the Thevenin resistance. And the low reactant has to be equal to the imaginary part of the low resistance. So in other words, ZL must be equal to ZTH, the conjugate of this expression. So right now we have already proven two cases. Case one is with purely resistive law, and case two is this one. This one. And finally, we end up with this. So let's summarize what we have learned. And according to what we have derived, what we have analyzed, for maximum power transfer to occur, for maximum power to be transferred to the low. We have two cases. Case one, purely resistive law. In this case, ROL must be equal to the magnitude of VTH. And case two, VL is equal to RL plus JXL. So in this case, we can briefly say VL is equal to the conjugate of the Thevenin system. So this is the conclusion we have drawn for this course, for this chapter. If you have any question, please leave your questions to the comment section of this video. Thank you very much for your attending this video lectures. Have a nice day.